Good morning, dear students. In the last class, we have learned a lot about the introductory ideas on surface chemistry, lesson number 10. And in particular, we learned a lot about the concept called as adsorption. I think you are very familiar with the term. Today, we are going to discuss about the first C. The other day I mentioned surface chemistry talks about C square. That means the first C is going to discuss about catalyst. And the second C will be learning more on colloids. In catalyst, we are going to discuss about the types of catalysts and what are catalysts and catalysts, the influence in any of the chemical reaction. In 1836, Berzelius, the scientist, he identified some of the chemical reactions by adding little bit of an external material, external substance, maybe a metal or a solid. They started going with the increased rate. I mean to say, the word rate refers to speed of a chemical reaction. This was a big puzzle for him. Later on, he identified the molecules which he added externally. They started loosening the bonds between the reactants, and they made the process of a chemical reaction feasible. So that was the reason for the increase in the speed. And he started naming catalyst because kata means holy, laying in its loosen. Then in Greek language, catalyst means it will loosen the bonds. That was the idea. And later on they found, other scientists, sometimes catalyst is retarding the speed of the reaction. That means it is decreasing the speed too. Now if you refer to our textbook, they have given the definition for the word catalyst in a very, very specific manner carefully. That means sometimes the catalyst can increase the reaction and sometimes the catalyst can decrease the reaction too.
Okay, so same deal here. We've got some hydrogen peroxide, 35%, some Dawn dish soap. I'll just add the dish soap into there, and I'm going to give you the honor this time, Tony.
Excellent.
Of adding the catalyst. Now, wait just 1 second. I'm going to take the cap off. I'm going to give this to you. Let me swirl this around a little bit. Hydrogen peroxide, soap, catalyst. Go ahead and pour it in. Let's see what happens. Just dump the whole thing in. We release the oxygen inside, and you can see we generate lots of foam. It's a giant blob of oxygen-filled, soapy foam, which is really cool.
It is. It's like.
Let us take our home even. You use your cycle for the travel. Unfortunately, this is the lockdown season. We are not using our cycle, and for the next 10 days we are not using. And after that period is over, we try to take our cycle for a ride. Earlier it was a very smooth ride for us. We felt happy riding the cycle. Since we never used it for the past 15 to 20 days, it may give us a little more trouble. You know the reasons why? Because the metallic parts would have rusted and the friction would have developed. Now the cycle may find it odd for us to move. Now what is the solution? You can apply a lubricant, maybe a grease or an oil, to the moving parts of the vehicle. If you do so, naturally the speed of the cycle will get increased. That is, you can exert a little pressure, little effort for movement of your cycle. You can take now, just for example I am saying, this lubricants as a catalyst for your cycle. The same situation, imagine one of your friends is suggesting you can use a little of sand for increasing the speed in the moving part of your cycle. If you try the same, and the opposite reaction will happen. You know what I mean to say? That means instead of increasing the speed of the movement of the moving part of the cycle, its movements will get reduced. So now I think you may be able to understand the difference between two things. In catalyst, we have to talk about a positive catalysis and a negative catalysis. That means a positive catalyst will increase the rate of the reaction, whereas a negative catalyst will decrease the rate of the reaction. So choosing a catalyst, we should be very careful whether to go for a positive catalyst or to go for a negative catalyst. Now, it's a time to learn about types of catalysis reactions. The catalytic reactions can be classified into two major types. The first type is homogeneous catalysis reactions, and the second type is heterogeneous catalysis reactions. What are homogeneous catalysis reactions? I think, boys, from the name you can understand the meaning. Homogeneous, we are talking about same. What do I mean by same? In any of the chemical reaction, you have the left hand side, we talk about reactants. We talk about the right hand side called as products. You know very well, they named as reactants because they react. They literally go and collide over the next reactant, and then they get produced, products are being produced. During the time, the reaction may go with a little slower rate. That means the reaction may be with a very slower speed. At that time, we may be adding a catalyst. Now the catalyst will play a wonderful role of making the reactants to react faster to produce the products. In such case, if reactant is in gaseous form and the product is also in gaseous form, we choose a catalyst for this reaction that is also in gaseous form, then we talk about homogeneous catalysis. All the three things, reactant, product and the catalyst, are in the same phase, then we talk about homogeneous catalysis. Let me give you an example. We try to prepare sulfur trioxide SO3. One of the reactant is SO2, the other reactant is O2. It is very obvious. SO2 is a gas, oxygen is also a gas, sulfur trioxide is also a gas. This reaction takes place in a very slow rate. If you want to increase the rate of this reaction, what is your next move? You have to have a catalyst. For example, we are using NO, nitric oxide. This nitric oxide is also a gas. This will increase the rate of the reaction. Now if you closely watch this example, 2 times of sulfur dioxide gives 2 times of sulfur trioxide, where sulfur trioxide, oxygen or the reactants, they are in gaseous phase. Product is also in gaseous phase, and the catalyst added nitric oxide is also in a gaseous phase. So this is the explanation for a homogeneous catalysis reaction. Now we are moving on to the next area called as a heterogeneous catalysis reaction. For the same reaction, heterogeneous catalysis, we can go for the same example. So 2 times of sulfur dioxide joins with the oxygen to give 2 times of the sulfur dioxide. If you take the same example, your learning becomes easier. Now sulfur dioxide is in gas phase, oxygen is in gas phase, sulfur trioxide is also in gas phase. For this particular reaction, we are going to add a catalyst, that is V2O5, that is vanadium pentoxide. This particular porous vanadium pentoxide is in a solid state. The catalyst added alone is in different phase. All these three are in the same phase, but the catalyst added is in a different phase. Then we talk about a heterogeneous catalysis reaction. You can quote so many examples. Even you can go for Haber's process of manufacturing ammonia. Ammonia manufacture is a very important process because our country is an agriculture-oriented country. India, we have to talk about more of Haber's process and preparation of ammonia because we have to prepare fertilizers like urea. So ammonia's presence is very, very important. For Haber's process, we have to take hydrogen and nitrogen. So that gives rise to ammonia. This is Haber's process. Where, as you know, dear students, this hydrogen is in gas phase, nitrogen is also in gas phase, and the ammonia is also coming out in gas phase. Is a typical equation of our reactant and products, all of them are in gas phase. We have to find one of the catalysts for this reaction. So we go for finely divided ion. That ion is in what state? That is in a solid state. Now this is another example for a heterogeneous catalysis reaction. Like that, so many examples we have in our textbook, you can refer them. So we have to concentrate these areas for our 2 marks and 3 marks. Beginning we learn something about catalyst, the definition for the catalyst, and the process of increasing the speed of the reaction. We learned it as catalysis. That may be another 3-mark question. And we learned something about positive catalyst and negative catalyst, and we learned about the types of catalysis reaction, that is homogeneous catalysis and heterogeneous catalysis. Our next objective is to learn about what are the characteristics of a catalyst. So every catalyst is having some characteristics. So those characteristics will decide the nature of the reaction. And the commonest behaviors of catalyst is, we have to talk elaborately about characteristics of a catalyst. The first catalyst characteristics is the catalyst is always taken in a very, very small quantity. A pinch of a catalyst is enough for any of the chemical reaction to take place. And even you would have seen some of the chemical reaction, for example, hydrogenation of oil, vanaspati preparation process. We go for a small addition, a small pinch of the metallic finely divided nickel is added. So a small quantity of the catalyst is more than enough for carrying out a chemical reaction. That is the first characteristics. The second characteristics is the catalyst will have some physical change. That may be possible. For example, if you take a catalyst, maybe the nature of the catalyst, the color, appearance of the catalyst, maybe before the start of the reaction with a different color. After the end of the reaction, it may have different color. So the color and the physical nature of the catalyst may change, but there should not be any change in mass and the chemical composition of the catalyst. So this should not catch. The change in these two behaviors are not accepted in a catalyst. And a catalyst cannot initiate a reaction. So what do I mean by this word initiate? A reaction is not at all taking place. I am adding a little of the catalyst. So immediately the reaction starts. That is not the behavior of a catalyst. the catalyst behavior is already a reaction is taking place with a slower rate. Now by the addition of a catalyst, the speed of the reaction may increase. So initiation is not the behavior of a catalyst. And the next behavior is the catalyst can be got at the end of the reaction. At the end of the reaction, you can get back the catalyst. So you can say the catalyst can be regenerated. It's a beautiful thing. After the reaction is over, you get back the catalyst and wash it and reuse it. So this is the end of the reaction, the catalyst will get back. And the catalyst should not change the nature of the product. Nature of product shouldn't be changed. That means for a particular reaction, before addition of the catalyst, the formation of the product is different. After applying the catalyst, a new type of product is formed. So that may not happen. Okay. So the nature of the product may not be changing. The next one is if you go for an equilibrium reactions. In equilibrium reactions, reactants will give products. After some time, products will go in a reverse direction to give back the reactants. In equilibrium reactions, the addition of catalyst will increase the speed of the reaction. That is, attainment of this equilibrium state can be enhanced, but the catalyst job is not to change the position of the equilibrium. Position of the equilibrium of the product formation cannot be changed by a catalyst, but instead it may be increasing the process of attainment of the equilibrium at a faster rate. So these are the behaviors of a catalyst. So the next thing we have to learn is about the behaviors so we learned a lot about the catalyst and the characteristics of catalyst. So now we have to learn certain other types of catalyst and their behavior. One such behavior is we are going to talk about promoters. What are promoters? Promoters are the substances which will increase the activity of the catalyst. You can say catalyst for catalyst. What is the meaning? The same process will take Haber's process so that your equation learning can be reduced. In Haber's process, 3 molecules of hydrogen joins with 1 molecule of nitrogen to give rise to 2 molecules of ammonia. This is Haber's process. In Haber's process, we used a catalyst called as iron. As you know, iron is an heterogeneous catalyst. It is in solid state. All others are in a gas state. And in this process, for example, I am giving you the process of manufacturing ammonia is taking place at a very slower rate. This just the values I am giving are the example values only. Maybe it take place in 20 hours time. I am adding a catalyst ion. Now what is the nature of the catalyst? It will increase the speed of the reaction. So the catalyst will increase the speed of the reaction, thereby after adding ion, the time of producing ammonia has come down to 2 hours. That shows catalyst is a positive catalyst, increase the speed of the reaction. Now even this timing may be too much for the preparation of ammonia, because we have to prepare a huge quantity of ammonia and industrial cost has to be reduced, so that the scientists have found out one more material called as MO. I think boys you would have seen in the transition elements, molybdenum can be used as a catalyst. Now already a catalyst is added that made the reaction to proceed in a faster rate. At present we are adding one more substance, a second material. Now the second material, molybdenum, will increase the activity of iron. Thereby the time of preparation of ammonia can be converted in 20 minutes. So now, why are they using the word called as promoter? Molybdenum is the promoter for this process. It enhances the activity of the catalyst ion. So this is called as promoter. Promotes the activity. That's why they named it as promoters. Next term we have to learn is catalytic poison. Don't be worried about the term poison. And they do the same job only. If we can take the same example for your understanding, the same Haber's process of manufacturing of ammonia. In that process, we use hydrogen and nitrogen, and the catalyst is iron, and we produced ammonia at 2 hours time, this for example. And instead of adding molybdenum, if we are adding hydrogen sulfide as the second material for the same reaction, this hydrogen sulfide will go and poison the iron catalyst. Thereby, the speed of attainment of reaching the ammonia preparation in 2 hours can be increased furthermore. Maybe it may be obtained in 8 hours. This for example. So a material which is added will go and decrease or retards the activity of a catalyst supply. Then we talk about catalytic poison. The next term we have to learn is autocatalyst. What is an autocatalyst? I think from the name of the word we can understand. Automatic. Yes. In the process of ester hydrolysis, ethyl acetate you can take, we go for hydrolysis reaction, addition of water, and there is formation of acetic acid and the ethyl alcohol. This is a well-known equation to you. Acetic acid and the ethanol will be the product. So in this particular reaction, one of the product formed, see these two are reactants, and acetic acid is one of the product, is on the right hand side. So the beginning of the reaction will go little slower rate. Once one of the product is formed on the right hand side, automatically the reaction will receive now the catalyst for its own reaction and start going in a faster rate. So one of the product form, when they ask in a public exam, if you miss this word, one of the product formed during the course of the reaction will increase the speed of the reaction, they may not be giving mark. As also in public exam, particularly in chemistry, when we go for public evaluation of your answer papers, the teachers who are correcting are very particular with the keywords in chemistry. That's in surface chemistry lesson, there are many questions or many areas where the keywords play a vital role. For example, in this case, and what is an autocatalyst? One of the product formed during the reaction. Instead of writing product, if you write reactant, you may not be getting mark. So you should be very cautious when mentioning the required words in your answers. So this is about autocatalyst. And as usual, the next one is negative catalyst. So what is a negative catalyst? Negative catalyst will decrease the speed of the reaction. For example, we go for H2O2. I hope boys you would have experienced this material in hospitals. This is used for cleaning the wounds. And hydrogen peroxide will decompose. If you open the bottle of hydrogen peroxide container, and then after some days you may not be having the action of hydrogen peroxide because the oxygen which is doing the action of disinfecting the wounds will evaporate out. Okay, will escape out. So, in the presence of glycerol, the speed of releasing oxygen will get reduced. Then we talk about negative catalyst. So, in catalyst types, we have learned about promoters, catalytic poison, autocatalysts, and negative catalysts. Next thing what we have to learn, now we have a big interest to learn about catalyst now. By adding a little material, the speed of the reaction is increased. What is the chemistry behind? So that we have to learn by understanding the theories behind this catalytic activity. So next part we have to learn about theories of catalysis. So in theories of catalysis, our main concern is we will be talking about two types of catalysis, homogeneous and heterogeneous. So the theories in particular, theories of catalytic reaction, the first theory is intermediate compound formation theory. So you can think of ICFT and A. What is ICFT? Intermediate compound formation theory of catalytic theories of catalyst. This is well known term to you. We talk about adsorption. So adsorption theory. And intermediate compound formation theory, I will explain you with a very known example. You might have used a mobile phone, Nokia phone. So the slogan or catchy slogan they give for Nokia in the advertisement is connecting people. Yes. Now, to explain about the intermediate compound formation theory, let us take that for our support. What's it? You are in Salem. For example, you are reactant A. You have to talk to your friend in Chennai. He is B. And both of you talk and you have some discussion, that is a product formation AB. So this is what is the expectation. And since we are in Salem and he is in Chennai, and you cannot have a conversation literally because it's too long distance. So you are getting help from Nokia now. Maybe a phone, mobile phone. So what happens here? This is the catalyst. First you in Salem link yourself with a mobile phone. That is the catalyst. C now is the catalyst. After linking with them, now the mobile phone will make a connection to B, your friend who is in Chennai. Now the contact between A and B will be done. You will have a discussion with your friend and you will learn about the situation in Chennai. After your discussion is over, then you will disconnect the mobile phone and the mobile phone is freed from you. That is the job of a catalyst. So during the reaction, the conversation was very slowly possible or not possible at all, or literally you can say it is slowly possible, and a catalyst will come and increase the activity between you, form the product, and catalyst will be regenerated at the end of the reaction. You can get back the catalyst. So this theory we refer it as intermediate compound formation theory. So if you want to learn it in the equation form, A reacts with B to give AB. AB is the expected product. For this reaction I am trying to have a catalyst now, C. First, A and C will have interaction to form an intermediate. Now AC is called as the intermediate. This intermediate will react with one more reactant B to form the product AB. See, this A and B will react. Who is now not important for us is the catalyst. Catalyst can be regenerated. So that's why in all these theories of catalysis, they are talking about energy of activation or activation energy, the nature of the catalyst added, or the main job the catalyst added to reduce the activation energy. I can quote you the example. If you are going in a road with a cycle, and what happens, in front of you there is a huge speed breaker. So you are in reactant side, you have to reach the product side. The barrier is a speed breaker. So this speed breaker height is called as the energy barrier or energy of activation. Obviously you have to cross this energy barrier, then only you can reach the product. That is the science. And unfortunately the speed breaker is huge in nature. So there is one methodology possible, that is, if the energy of activation, that is, it is reduced a little, then from reactant side product formation is easily possible. So the catalyst job will be very important only in this place. So the catalyst job is to reduce this energy of activation and make it very small, so that you would have seen, boys, when the speed breaker is very huge, and obviously your speed of going in cycle will get reduced. And if it is minimized, then you can go a little faster. So this is the main advantage of using a catalyst. Catalyst will increase the speed by reducing the energy of activation or activation energy. So this is the first theory we learned about intermediate compound formation theory. If you want the same thing with an explanation, with one of the examples well known to you, would have learned in 11th standard 2. The reaction is called as Friedel-Crafts reaction. What is Friedel-Crafts reaction? Friedel-Crafts reaction, we take benzene, or I can take C6H6 benzene, reacts with acetyl chloride, acetyl chloride, to give you a product C6H5COCH3. A Friedel-Crafts reaction of acetylation. Then you can take even acylation process, a methyl chloride reacts, and there is a formation of, just to make it easier, formation of toluene, methyl benzene. And here, benzene is one of the reactant. I can say benzene is B. And methyl chloride is one of the reactant, say A. And our product is toluene, methyl benzene. For this reaction, we are going to add a catalyst, that is anhydrous aluminum chloride, AlCl3. Anhydrous aluminum chloride. This anhydrous aluminum chloride will help us to reach the product. How? First, this is catalyst C will react with A. A is methyl chloride. So CH3Cl plus aluminum chloride, AlCl. These two will react to form an intermediate. The bond breaks and chlorine gets connected with aluminum chloride, and CH3 plus and AlCl4, aluminum chloride, AlCl4 minus. This is called as AC, that is intermediate. Now this intermediate is going to attack one more reactant B, that is B is C6H6, I can write C6H5 and H for your easy understanding. That reacts now with the intermediate formed. So this hydrogen will react with the chlorine of AlCl4 minus, thereby these two will form as a product and aluminum chloride will be removed and hydrochloric acid will be removed. The final product can be C6H5CH3, that is methyl benzene phosphate. So there we can understand the importance of a catalyst, and this is the first theory called as intermediate compound formation theory. In intermediate compound formation theory, one of the reactant will react with the catalyst to form an intermediate. That intermediate will react with another reactant to form the product. This is the first theory. Dear students, just now we have learned about intermediate compound formation theory of catalyst. But this theory was not successful for every field because that theory was having some limitations. The limitations are this theory could not explain to talk about the promoter concept and catalytic poison. And also it could not explain the heterogeneous catalysis reactions. So Langmuir, the scientist, is coming out with a new theory of adsorption theory. From the word you can understand adsorption. We learned a lot about adsorption. Adsorption is a surface phenomena, and that too it contacts the surface of the catalyst. So that is the reason why adsorption theory is otherwise also called as a contact theory of catalysis. Okay, so how to understand? It takes place in 5 different steps. Let us discuss them in step-by-step manner. First, second, third step, fourth one, and fifth step. Let us take an example of hydrogenation of alkene. Let us take a simplest alkene, that is CH2 double bond CH2. This is called as ethylene molecule, ethene in IUPAC. And this ethylene molecule has one sigma bond and another one is a pi bond. Out of these two bonds, the pi bond can be easily broken, and you can add on either side hydrogen atoms. Then an unsaturated alkene, double bonded alkene, will get converted into a saturated hydrocarbon. I hope boys have learned in 11th standard about hydrocarbon. They have only carbon and hydrogen. Now it has only single bond, so an ene gets converted into ene. Alkene gets converted into alkane. Ethene gets converted into ethane. This is hydrogenation reaction, addition of hydrogen. But this is a very slow process. To enhance the speed of this, we are adding nickel. Now nickel is acting like a catalyst for this reaction. So what this nickel is going to do? The first step Imagine this is the surface of Ni, nickel catalyst. One of the reactant for that is hydrogen. So from hydrogen is available onto the surface of a nickel, it is got connected to the nickel surface. So the first step, diffusion of the reactant towards the surface of the catalyst. So they go in contact, that's why it's called as contact catalyst reaction, in contact with the catalyst. So an ethene molecule which is having double bond will go closer to the catalyst surface. Now step 2, it gets attached by a partial chemical bonding. Hydrogen 2 gets attached. Now step 1, diffusion, and step 5, you can take this way. First step, the reactant molecules are going towards the surface of the catalyst, and the last step, the product formed, that is the ethane formed, will go away from the surface of the catalyst. So that way you can understand easily first step and last step. Coming towards catalyst, going away from catalyst. The next step is, since they are closer, that is hydrogen and the ethane are closer, they will try to form an activated complex AC. So activated complex will reduce the energy of activation, thereby the intermediate complex, activated complex is being formed. Then the formation of product will take place in the third step. So there is a formation of a product take place. Once the product is formed, there is no need of this catalyst nickel. So the products will get dissolved or detached from the surface of the catalyst. So they get dissolved here. First step, diffusion. Second step, joining to the surface and forming an activated complex. An activated complex gets converted into a product. Then the product is getting dissolved from the surface, and finally the products leave the place of the catalyst and diffuse as product. This is how the adsorption theory works.
According to the modern adsorption theory, free valencies are present on the surface of the solid catalyst. The catalysis process involves 5 steps. The first step involves diffusion of the reactant molecules towards the surface of the catalyst. The second step involves adsorption of the reactant molecules on the surface of the catalyst, followed by the formation of weak bonds with the catalyst due to the presence of free valencies. The third step involves a chemical reaction between the reactants and the catalyst, forming a complex that is essentially the product attached to the catalyst. The fourth step involves desorption of the product molecules from the surface of the catalyst as it lacks affinity for the catalyst surface, making the surface free and ready to interact with another reactant molecule. The last step involves diffusion of the product molecules away from the surface of the catalyst. The modern adsorption theory successfully explains that only a small quantity of the catalyst is sufficient for the reaction, as the catalyst is regenerated in the reaction, and that at the end of the reaction, the mass and the chemical composition of the catalyst remains unchanged.
The catalyst, the very, very important word we have to talk in catalysis is active centers. What are active centers? any of the catalyst, it is having on its surface some of the very, very active sites. Always the catalysts are not very smooth, like a ball dress or shiny balls. They are made up of peaks, cracks and edges of the catalyst. The activity will be very, very sharp and the catalytic activity will be very, very high. Because in those areas there's unsaturation of the energies will be there. Those areas only will try to attract the reactant towards them because they are activated places, and they will make the reaction of reactants possible, and they will go for the activated complex and the products are possible. So that's why the scientists, whenever they try to add a catalyst, they add it in the form of broken pieces, or they powder it and add. One way the surface area will get increased, because of that the catalytic activity will be more. Other thing is only when the catalyst is added in an irregular form, the product formation will take place at a faster speed. So now the active centers gets increased. Now you can talk about two important phenomena we learned. Promoters and active centers. Both are contradicting technologies. What are they? A promoter will enhance the activity of a catalyst, whereas a catalytic poison will retard the activity of the catalyst. How come a promoter can enhance the activity of the catalyst? We can get answer from active centers. When active centers are more, that means the second material goes and enhances the more of active centers in a catalyst, then product formation is possible at a faster rate. Instead, for example, in Haber's process we used molybdenum. Molybdenum will go and create a lot of active centers in iron catalyst. Instead of molybdenum, you add hydrogen sulfide. The hydrogen sulfide will go and block the active centers of the catalyst. Thereby the catalytic activity will be decreased. So this is the next part of our lesson. We learned about catalyst types and the theories of catalysts, and we learned the last part of this discussion about active centers. So in the next class we will be learning about enzymes which are acting like catalysts.